So suppose x1, x2, xn are IID from exponential location scale model with commonly gave PDF. F theta x, which is 1 by sigma e to the power minus x minus mu by sigma. If x is greater than mu, 0. If x is less than mu. It says all the three things. Find MRI. So it's a good problem. I'll tell you in what sense. Sigma under the loss function. Which is mod of A by sigma minus 1 to the power b. P is 1 or 2. B. Find MRI of mu under the loss function L theta A, which is A minus mu by sigma whole square. The C problem, which I did not do because in the location scale model, I only dealt with estimation of mu or sigma. C part says that find MRI of mu plus sigma, which I am denoting by eta, under the loss function S. So what you'll see is for part A and part B, we already have a theory. It is only the part B. Part C, we have to develop a separate theory for that and see whether invariance principle applies or not. So first note that my joint PDF should be belonging to the location scale family. So note that my f theta of x1, x2, xn, f theta I'm denoting by that, so let me write down that as a star, f theta star, which is joint PDF of x1, x2, xn. This is nothing but because of independence, 1 by sigma to power n e to the power minus summation I is equal to 1 to n xi minus mu by sigma. Now everything I have to write down in terms of xi minus mu by sigma. So x is greater than or equal to mu can be written as x minus mu is greater than or equal to 0, or x minus mu by sigma is greater than or equal to 0. So this whole I can write down as xi minus mu by sigma is greater than or equal to 0, I is equal to 1 to n, 0. Otherwise, so this can be written as 1 by sigma to the power n product or 1 by sigma to the power n f of or f naught of or f star of, if you want, yeah, f star of x1 minus mu by sigma. Now x belongs to whole of Rn. Where is what is my f star of T1, T2, Tn? My f star of T1, T2, Tn you get from here. This is sigma to power n goes, so e to power minus summation I is equal to 1 to n Ti, if each Ti is greater than or equal to 0. And this is 0 otherwise. So it is a location scale family. So if it is a location scale family, I know what is the group of transformations under which this problem is invariant, or this class of probability distributions is invariant, because the same class of transformations I'll use for problem C. So G is nothing but collection of all those GBCs, says that B is positive, C belongs to R, and what is my GBC of x1, x2, xn? This is bx1 plus C up to bxn plus C. X belongs to R. B positive, C belongs to R. Now we have seen that this class of probability distributions is invariant under this affine group of transformations with induced group of transformations on the parameter space as G bar. And what is why G bar BC of mu sigma? It is same as B mu plus C, B sigma, B positive, C belongs to R. Mu sigma belongs to theta parametric space, which is R cross 0 infinity. Okay, so this is the background which I wanted to give. The first two problems have already developed the tools. In the case of sigma, what I have to do is, first, I try to see whether a complete sufficient statistics exist or not. So, A part, it is a 2-parameter exponential family. From last course, you know that the complete sufficient statistic is x1, smallest order statistic, and summation xi minus x1. So, is complete sufficient. W was ancillary, so things are simpler in this case. So the only thing now, next thing I have to do is I have to find an estimate of sigma, which is scale invariant. Now you know that this turns out to be something which is good for location. Constant time, this looks like a good estimator for sigma because xi minus x1 measures the split. So I take my delta naught x to be summation I is equal to 1 to n xi minus x1. I have to make sure that the delta naught which I choose is scale invariant. So what I have to choose for sigma? So delta naught of bx1 plus c, bxn plus c would be how much? So bxi plus c would come, then minimum of bx1 plus c, bxn plus c. Since b is positive, it would be same as b of minimum of x1, x2, xn plus c. C gets cancelled, b again comes outside, so it becomes b of delta naught of x1, x2, xn. So what does that say? This means your delta naught belongs to di. Belongs to di. So then by a result, what does follow? So MRI is delta star x, which is nothing but delta naught x by u star, where u star minimizes psi u, which is E01 W of delta naught x by u. Now the loss function is mod of a by sigma minus p to power p. Sigma is 1 because E01, E sigma is 1, so that is expected value of mod of delta naught x by u minus 1 whole power p. So you have to consider case p. Now note that delta naught x What is the distribution of this from last course, you know? Under mu is equal to 0 and sigma is equal to 1, this has gamma n minus 1. Gamma n minus 1. So gamma, standard gamma distribution with say parameter n minus 1. So you can now calculate it one by one. So let me calculate it. For p is equal to 1 and then p is equal to 2. So p is equal to 1. Psi u is nothing but expected value of delta naught x, which is gamma n minus 1. So gamma mod of gamma n minus 1 by u minus 1 p is 1, which is nothing but 0 to infinity mod of t by u minus 1, and then gamma density at point t, gamma n minus 1. So e to power minus t to the power n minus 2, gamma n minus 1, which is nothing but factorial n minus 2 dt. So I have to minimize this. So what I do is I break it in integral in two parts so that I can get rid of this modulus. So t less than u. So t is less than u. So 0 to u. T is less than u, then that means t by u is less than 1. So this is negative, so it becomes 1 minus t by u, e to the power minus t, t to the power n minus 2, factorial n minus 2 dt, plus u to infinity. Now t is greater than u. So that means t by u is greater than 1. So it becomes t by u e to the power minus t, t to the power n minus 2 by factorial n minus 2 dt. Other way, what you could have made the translation t by u as z, and then you could have done it, and then you could have broken it. Doesn't matter, one and the same thing. So now I try to take the derivative of this with respect to u. Now one thing, you should note that I have taken u to be positive because t less than this. If u was negative, what does that mean? If u was negative, this itself would have been negative because u is negative, so this would have been minus of, right? If u was negative, then you see that u negative cannot minimize this. Just try to look at it. It is just trivial to look into it. If u is negative, then the things would be different. I can come to that later on. So this for u positive. So I try to see what is a derivative. So derivative first is, you have to use the implicit function theorem. So first this goes over here, so u by u minus 1, that doesn't contribute anything. So only thing which will contribute is from here. So if I take the derivative, that becomes 0 to u 1 by u square, right? Minus t by u, so t by u square t, so that becomes e to the power minus t, t to the power n minus 1 by factorial n minus 2 dt, all right? The first part where this goes over here because that anyway is taken care of. Similarly over here, when this goes over here, that part is 0, so only this part would come. So minus 1 by u square u to infinity t, sorry, t is remaining, so that can go with that. So e to power minus t, t to power n minus 1 by factorial n minus 2 dt. So this can be written as 1 upon factorial n minus 2, 1 upon u square. Is that okay? 0 to u, e to power minus t, t to power n minus 1 dt, minus 0 to infinity, sorry, u to infinity now this is greater than 0. I see when this function is increasing. This function is increasing if and only if 0 to u e to power minus t, t to power n minus 1 dt is greater than u to infinity e to power minus t, t to power n minus 1 dt. I can divide both the sides by factorial n minus 1. The thing don't change, so that it becomes a density. Now it is a PDF of a gamma n minus 1. So it is a probability that gamma n minus 1 is less than u. This is a probability that gamma n minus 1 is greater than u. So this can be written as 1 minus 0 to u, because e to power minus t, t to power n minus 1 by factorial n minus 1 is a density, e to power minus t, t to power n minus 1 by factorial n minus 1 dt. So what does that mean? So let me write down this. Use this space here. So that means 0 to u e to power minus t, t to power n minus 1 by factorial n minus 1 dt is greater than half. So it is increasing if 0 to u is greater than half. So let me call this as a density of gamma n minus 1. So that means this is gamma n minus 1 u is greater than half. What is a gamma n minus 1? This is a distribution function of gamma with shape parameter n minus 1. That is equivalent to saying that u is greater than gamma n minus 1 minus half. So your psi u is increasing after u greater than gamma n minus 1 half, and before that it is decreasing. So your psi u looks like this. This is gamma n minus 1 inverse half. Before that, u less than 1, this would be decreasing, u greater than 1, this is increasing. So that means minimum is attained at gamma n minus 1 half. So u star, that means g n minus 1 inverse half, which is basically a median of gamma n minus 1. Standard gamma with shape parameter as magnet. So what is MRI? Delta star x which is xi minus x1 divided by gamma n minus 1, median of gamma n minus 1 half. So for all u greater than 0, I know that minimum is attained over here, and u less than 0 you can easily check. You see, if u is less than 0, what happens? just to, for completeness, for u less than 0. You see, for u less than 0, anyway, summation xi minus x1 divided by u, that would be a negative quantity. So that cannot be considered as an estimator of sigma, which is positive. But theoretically, if you want to show that it is u less than 0 will never give a minimum, you can look at psi u as becomes 0 to infinity mod of t by u minus 1 e to the power minus t to the power n minus 2 by factorial n minus 2 dt. Which is nothing but 1 by mod of u, right? Mod of u is nothing but minus 1 upon u, right? 0 to infinity mod of t minus u e to the power minus t to the power n minus 2 by factorial n minus 2 dt. Now, if you want, you can break this integral into two parts, t less than u and t greater than u. Now, t less than u will not make any sense because t is always positive. Sorry, u is negative. So t less than u, which is negative, will not make any sense. So t here is always greater than u when range is 0 to infinity. So that, or in other words, t minus u, because u is negative, t minus u is always positive. So this is same as minus 1 upon u, 0 to infinity, t minus u e to the power minus t to the power n minus 2 by factorial n minus 2 dt. This becomes minus 1 upon u. Then this is a mean of a gamma n minus 1, right? So mean of a gamma n minus 1 is nothing but n minus 1 minus u, right? Because that whole is a density. What does that become? It becomes 1 minus n minus 1 by u. So it is always an increasing function of u. So minimum would be at u is equal to minus infinity, which doesn't make any sense, right? Because the estimator you would like to choose is gn minus 1. Basically, estimator would like to choose to be positive, so would like that u star is always positive. So u taking negative does not make sense, and anyway, I get something very absurd if I choose u to be negative. Now, what happens in the case of squared error loss function? P is equal to 2. So I repeat everything for P is equal to 2. This is square, which is nothing but expected value of gamma n minus 1. So in this case, you know u star turns out to be how much? Expected value of gamma n minus 1 square divided by expected value of gamma n minus 1. Expected value of gamma n minus 1 is nothing but gamma n minus 1 square n minus 1 into n divided by expected value of gamma n minus 1 is just n minus 1. So it becomes n. So MRI for P is equal to 2 is delta star x, which is 1 upon n now let's consider estimation of mu. So note that here in the estimation of mu also, the Basu's theorem is applicable because I have a complete sufficient statistic, which is x1 and summation xi minus x1. So for the estimation of mu, what I have to do now? So that conditional expectation is not involved over here because W is ancillary, x1 and summation xi minus x1 are complete sufficient. So I can just manage without conditional expectation. So I need to just find estimators based on complete sufficient statistics xi minus x1. So delta naught is a estimator based on complete sufficient statistic for mu. So I can take delta naught x to be x1. It is an estimator of mu, affine equivalent. Delta 1x, I can take summation I is equal to 1 to n xi minus x1. What I have to check? Delta naught is a affine equivalent estimator for mu. So for that, what I have to check is delta naught of bx1 plus c, bxn plus c should be same as b of delta naught x plus c. So it would be a delta naught of bx1 plus c, bxn plus c would be the minimum of all this. But since b is positive, minimum of this is same as b times minimum of x phi is plus c, which is same as b times delta naught of x1, x2, xn plus c. So delta naught is a affine equivalent estimator of mu. What I have to check for delta 1? Same thing, it should be a affine equivalent estimator for so minimum would be again bx1 plus c, xi is bxi plus c, cc gets cancelled, b comes outside, so it becomes b times delta 1 of x1, x2, xn. And that is what I wanted, my delta naught and delta 1. And delta naught and delta 1 are function of a complete sufficient statistic. So what is MRI? MRI is nothing but which is delta naught x minus u star. Here u star is not going to depend on W because of applicability of a Basu's theorem, delta 1x, where u star minimizes psi u, which is E01 W of delta naught x minus u delta 1x. But here loss function is given to be a minus mu by sigma whole square. So my Wt is given to be t square, because that is how the loss function is, squared error. So this is same as E01 delta naught minus u times delta 1 whole square, which is u square E01 delta 1 square minus 2u E01 delta 0 delta 1 plus E01 delta 0 square. All right. So I take the double derivative. Double derivative turns out to be 2 times E01 delta 1 square, which is positive. So double derivative is positive. So that means if I put first derivative is equal to 0, I get the minimum. So minimizing u, so u star turns out to be the where derivative is 0. So that means 2u times this minus 2 times this is equal to 0. So that means u star turns out to be E01 of delta 0 delta 1 delta 1 square. And what is that? E01. Delta 0 was x1, and summation I is equal to 1 to n xi minus x1. By E01 of summation I is equal to 1 to n. Whole square. Now, in the exponential case, I know that these two, x1 and they are independent. They are independent. Right? You can apply Basu's theorem even to show that they are independent. And this you must have done in your last course. Okay? So, for example, you first fix sigma. If first sigma, fix sigma, then x1 is complete sufficient for mu. And this is ancillary for mu for a fixed sigma. So, for any fixed sigma, they are independent, and these statistics do not depend on sigma. So, that means for any sigma, they would be independent. So, this is same as E01 of x1, E01 all right. So, you also know that in the exponential case, the minimum order statistic has a again exponential with proper standardization. That means n times x1 minus mu. So, n times x1 minus mu, I am talking about 0, by sigma is equal to 1. This has exponential 1. So, what does that mean? That means expected value of under 0 and 1 n x1 is nothing but expected value of exponential with parameter 1, which is 1. This implies that E01 of expected value of x1 is nothing but 1 upon n. E01 under mu 0 and sigma 1, you know that this is gamma n minus 1. So, this is E01 of gamma n minus 1, which is nothing but n minus 1. E01 of summation I is equal to 1 to n xi minus x1 whole square is nothing but expectation under mu is equal to 0 and sigma is equal to 1 of square of a gamma n minus 1 random variable. And this you know is nothing but n into n minus 1. So, U star which you get actually, yeah, U star is nothing but how much? 1 upon n and 1 upon n square. So, what is your MRIE? Which is x1 minus 1 upon n square, summation I is equal to 1 to n. Now, in this case, if you recall, your UMV turns out to be exactly same, that except that in place of 1 upon n square, you get 1 upon n into n minus 1. In general, if I put in place of 1 upon n square any constant c, this estimator is still invariant for mu. You can see that delta star of bx1 plus c, bxn plus c would be b of delta of x1, x2, xn plus c. So, among all such estimators, you can directly say using principle of invariance that this estimator has the smallest mean square error. All right? Let me just quickly test the third part. Now, whenever I am applying a principle of invariance, the first thing I have to see is class of probability distribution is invariant. Now, in this case, class of probability distribution is invariant with G, which is Bx1 plus C, Bxn plus C. It induces a group of transformation B mu plus C and B sigma. So, whatever the statement is, I try to see where does that gets translated to. So, if you look at mu plus sigma under G bar or under G bar BC, where does this goes to? Mu goes to B mu plus C and sigma goes to B sigma. So, which is nothing but B of mu plus sigma plus C. Which is same as B times original xn plus C. So, my G tilde turns out to be G tilde and what is your G tilde BC from here? B times the original xn, B of A plus C. The way you had it for location invariant, for equivalent distribution of, so A belongs to A, which is whole R, B positive, C belongs to R. So, what is the property of my invariant rule for delta to be invariant? Delta is invariant if and only if delta of G BCX, which is Bx1 plus C, Bxn plus C, is same as B times for every B positive, which is same as the property of any estimator of mu. So, what does that mean? This says that let delta naught be affine invariant estimator of mu, and if delta 1 is any affine invariant estimator of sigma, then any affine invariant estimator of mu plus sigma so delta belongs to Di if and only if delta of x minus u star w of delta 1x and MRI in this case because w is ancillary. So, what is MRI? So, you have to see when loss function is invariant. L theta A should be same as L G bar B C theta is equal to A. So, that means L of, let me write down theta, mu sigma A should be same as L of B mu plus C sigma B A plus C for every theta belongs to theta, B positive, C belongs to R, and this is what exactly the property of your loss function of mu. So, what does that say? That means L theta A would be nothing but A minus eta whole square by sigma square. In fact, this means actually this implies that L theta A would be nothing but W of A minus eta by sigma. That is what it means. Now, this is of this type with Wt is equal to T square. So what is MRI? Eta is delta x, which is delta naught x minus u star times delta 1x, where u star minimizes psi u, which is E01 of the loss function. Loss function is nothing but E01 of A minus eta by sigma whole square. So that means delta star x I've written as delta naught x minus u times delta 1x divided by sigma is equal to 1 minus eta whole square. Eta is mu plus sigma. So under mu is equal to 0 and sigma is equal to 1, that is 1. All right. So what does that become? This becomes E01. So u square of E01 delta 1 square x minus 2u expected 0, 1 delta naught minus 1 into delta 1 plus delta naught minus 1 whole square. I again take the second derivative. I see second derivative turns out to be 2 times E01 delta 1 square x, which is positive. So the minimizing u would be where the derivative is 0. So that means u star turns out to be where derivative is 0. So 2u minus this is equal to 0. So that means E01 delta naught minus 1 delta 1 by E01 delta 1 square. But delta naught is x1, this is summation xi minus x1, and they are independent. So delta naught minus 1 and delta 1 are independent. So this becomes E01 delta naught minus 1 into E01 delta 1 divided by E01 delta 1 square. And what is that? E delta 0, we have seen it was n times exponential, it was 1 upon n minus 1. All right. E01 delta 1 is nothing but n minus 1. And E0 delta 1 square is nothing but n minus 1 into n. And how much that becomes? Minus n minus 1 upon n square. Is that okay? So what is your MRIE? Delta naught x, which is x1, minus u star, but u star again is coming with a minus sign, so it becomes plus n minus 1 upon n square, summation I is equal to 1 to n, xi minus x1. So this is what MRIE turns out to be. So this was a nice example in the sense that the first problem gave you the estimation of sigma under the affine group of transformation. The second problem dealt with estimation of mu under the affine group of transformations. The third problem, we did not develop any theory, but we could see that I can apply the invariance principle here also. And then I could also find the best invariant estimator. So tomorrow again I will take up few problems and I'll try to give you more insight how you can apply invariance into different situations, apart from the situations which we covered. So apart from the 3 situations which we covered, one was location alone, one was a scale alone, one was a location and scale together. So that's for the next time. So that's all for today, and thank you very much.